In the last video, I introduced the Mamba model and I compared it to RNNs as well as transformers. I also showed how the Blalock scan was enabling this very efficient parallel computation. This video is a very natural follow-up of the first one. I will explore the concept of backpropagation through time and all the engineering issues that appear when you try to model dependencies in very long sequences. This video is focused on Mamba, but the knowledge is definitely also applicable to RNNs and SSMs. I will also take this occasion to shout out to Alexandre Torres, the guy behind the MambaPy repository. I used it to train my Mamba models, contributed to the repo, and will continue to do so. Before diving into the main issues an engineer can encounter when performing backpropagation through time, we need to start the presentation by defining this concept on a typical neural network. This explanation is done with a recurrent neural network, but would be pretty much the same for an SSM and typically for Mamba, with the exception that some of the computation can be done in parallel across the sequence. The setting is the following. Inputs X are getting fed, the model encodes them into some states that get decoded into outputs Y. A loss is computed per output. The state persists some information in time. We define theta as the model parameters being used to integrate the contribution of tokens to the state, see X to S arrow, but also to define how the states persist in time, see the S to S arrow. Please note that in this animation, we greatly simplify the model. A typical Mamba model would have several layers of state. Also, S to Y is not parameterized. It's not realistic, but it would bloat the computation without bringing any conceptual value. So this is our setting. The total loss is very naturally the sum of the losses. Now let's see how we compute gradient to update those shared parameters. This is the backpropagation through time. Our goal is to compute the gradient of the total loss with respect to theta. Since the total loss is a sum, this gradient is also a sum, one term for each time step. The challenge is that theta appears at every time step, so each term must account for all the paths through which theta influences the time step's loss. So for the first time step, it's very straightforward. The gradient of L0 with respect to theta is just a chain rule applied along a single path, from L0 through Y0 through S0 down to theta. For the second time step, things get more interesting. The gradient of L1 with respect to theta has two contributions inside the brackets. The first is the direct effect, how theta influences S1 through the current input. The second traces back through the recurrence, how theta influences S0, which then influences S1. For time step 2, the pattern continues. Now we have three terms in the brackets, the direct contribution at S2, then a path back through S1, and finally the longest path all the way back to S0. Each additional step adds another term, tracing the gradient one step further back in time. So this gives us the general BPTT formula. For each time step t, we sum over all previous time steps k. The product term in the middle captures the chain of state-to-state Jacobians from step k to step t. This is the gradient flowing backward through time. Okay, so now we're done with the formulas. Hopefully this gives you a pretty good understanding of backpropagation through time. Now let's get a rough idea of how GPU memory behaves when we process chunks of inputs using backpropagation through time. If you're watching this, there is a high chance that you know how deep learning frameworks like PyTorch handle forward and backward propagation. During the forward pass, all the activations are kept in memory because they are needed for backprop. As backprop gets computed, the memory is progressively cleaned. However, BPTT chunk size conditions the length of the dependencies you are able to model. So if you process very short chunks, the model will be unable to encode into the state and information that would only be useful way later down the line. This is why we would naturally want to process bigger and bigger chunks. However, memory starts to become an issue. So where is the bottleneck? When you train a deep learning model, memory usage usually stems for three things: the activations, the parameters of the model, and the optimizer state. When you train, for example, a transformer-based architecture, you have this very cool tool from the UltraScale Playbook that enables you to visualize in a very easy way which of those three takes the most memory. And you can actually guess that when you train small models on very huge chunks or very huge sequences, the activations are the bottleneck. And typically when you train those very big models on shorter chunks, the model parameters and optimizer are the bottleneck. For our use case of training with backpropagation through time on a Mamba model, I took the example of a Mamba model with 130 million parameters. I tried to train it on sequence length of 10,000, and I can very clearly see an activation memory bottleneck. And it does make sense, especially for recurrent network type of models, as the same parameters are used over and over across time. But of course, the longer the sequences are, the heavier the activations are as well. When initially facing this issue, the idea that we could compute the sequence by chunks and run the full propagation through time across the chunks crossed my mind. Unfortunately, as you can see here, the memory still accumulates until the gradients start getting computed. So it does not really solve our issue. Truncating the long sequence and doing training steps on them one by one is definitely manageable in memory. However, it is not entirely satisfying either, as we fail to model dependencies from one chunk to another. We actually have another option. What if we run the forward and backward propagation chunk by chunk like before, but this time we maintain the state between the chunks? In terms of memory, it works perfectly. We can clear the memory at the end of each chunk and even do a parameter update. In this setting, the model will learn to make some use of the context it receives from earlier chunks, but it will not learn to encode in the state a piece of information that could prove useful in a few chunks. So, is it even possible to model very long-term dependencies with limited GPU memory? The answer is actually yes, using activation checkpointing. You know this method that trades compute for memory and is widely used in LLMs. Let me give you a quick recap of how it works. As we said earlier, during training, the forward pass stores activation at every layer, because the backward pass needs them for computing the gradients during backpropagation. That's expensive. Activation checkpointing saves memory by keeping only a few checkpoints and recomputing the rest of the activations on demand. Here we have 12 layers in 4 segments, with a checkpoint at the start of each. In the forward pass, each layer produces an activation, but only checkpoint activations, the yellow squares, are actually kept. The others are immediately discarded, and this repeats for every segment. By the end of the forward pass, we're storing just 4 activations instead of 12. Now the backward pass. Before backpropagation through a segment, we recompute its activation from the checkpoint. And that's the trade-off. We rerun part of the forward pass. Then gradients flow normally and we free the memory. Same process, segment by segment, right to left. Recompute from the checkpoint, backpropagate, discard. So peak memory stays proportional to one segment size plus the other checkpoints. So finding the right number of segments is actually key. The result is mathematically identical to standard propagation, same gradients, it's just computed differently. And with all gradients accumulated, we update the parameters as usual. We just saw the general theory behind activation checkpointing, but how does it look for a Mamba model? It's actually very much the same idea. We run the forward pass chunk by chunk, and we actually do not need to compute the outputs and losses. At each chunk boundary, we save the hidden state, that's our checkpoint. Everything else is discarded. The sequence still flows left to right, but we're not holding all 24 time steps in memory. The last chunk stays fully alive, states, outputs, loss, because that's where backpropagation starts. Then gradients flow backward through this chunk normally. Parameter gradients are accumulated, and then we free this chunk's memory. We also keep the first gradient of the chunk, and for the chunk before, we need those activation back, so we rerun the forward pass from the safe checkpoint. The hidden state at the chunk boundary gives us the exact starting point. And yeah, it unrolls again. We recover all intermediate state and then backpropagate through them. At the end of the backpropagation, we apply one parameter update from the fully accumulated gradient. In the end, the cost of activation checkpointing is roughly this one extra forward pass that enables us to not truncate our gradients, neither crash out of memory. In this presentation, I showed how backpropagation through time works, how and why it can be GPU memory intensive, and how to work around this issue. I hope that you liked this episode, and I'll see you in the next one.